So in this example, we're told the following information. Suppose that 1 out of every 100 people have some disease A. Suppose that we're also told there's a test and that it correctly identifies if you have the disease 95% of the time. Let's say it correctly identifies not having the disease. (92% of the time). And both of those are of the time. So, given all that, suppose that someone tested positive. What's the probability they actually have the disease? So, let's take a look at what we've got. First of all, I'm going to call the probability of having the disease A, and I'm going to say the probability of the test saying that it's positive, I'm going to call that T. So what sort of probabilities do we already have? Well, we've got the probability of A. If 1 out of 100 people have it, then that means the probability of this is 1 out of 100, or 0.01. Now, since probabilities have to add up to 1, if 1 out of 100 people have the disease, then that means that 99 out of 100 people do not have the disease. And so I have this not A. And that comes out to be 0.99. Now, we're not told the probability that the test tests positive in general or that it tests negative in general. What we're told is that a test correctly identifies us having the disease 95% of the time. So the way I'm going to write that in probability terms is that the probability that the test is positive, so I'm saying a positive test with a T, without a bar over it, given that they have the disease, is 0.95. So see what's going on here. A test correctly, so positive, identifies having the disease 95% of the time. So the probability I get a positive test given I have the disease is 0.95. Now the second thing is that the test correctly identifies not having the disease 92% of the time. So even though I say the test is correct, that doesn't mean that I'm going to have positive things here. You have to think about what's going on. If I don't have the disease, then a correct test means that I tested negative. So then this second line here, or third I suppose, is telling me that the probability that the test is negative, given that I don't have the disease, is 0.92. Now, what are we trying to find out? We're trying to find out what's the probability that someone has the disease if they tested positive. So that's basically flipped around. That's the probability that you've got disease A given that the test was positive. Well, there's a theorem for A given T which makes use of this flipped around backwards, T given A. And that would be sort of my clue that I want to use it. That theorem is Bayes' theorem. So if I write this out, it's the probability of T given A multiplied by the probability of A divided by the same thing, probability of T given A, but then add to that the probability of T given not A multiplied by the probability of not A. And to think about why this makes sense, we're asking what's the probability that I have disease A given that I tested positive. And now let's look at what we're having here. We're having the probability of giving a positive test given you have the disease, so that's what we're interested in. What's the probability I've got the disease? And then there's two possibilities. either I test positive and I have the disease down here, probability you test positive given you have the disease multiplied by you have the disease, plus the probability that you test positive given you don't have the disease multiplied by the probability you don't have the disease. So we're taking all possibilities, right? We know we have a positive test, so we only see positive t's everywhere. But all the possibilities are positive test got the disease, positive test don't have the disease. That's your sample space. The numerator is positive test got the disease, because that's what we're asking about. So what pieces do we need? We've got t given a. We've got a. We do not have t given not a, although we do have not a. So we need to figure out t given not a. Well, if you look at this right here, this is the probability I don't have, or let me rephrase that. This is the probability I test negative given that I don't have the disease. Well then, the probability that I test positive given that I don't have the disease, that's going to be 1 minus the probability that I tested negative given that I don't have the disease. Why? Because we're not changing the criteria. We're talking about not having the disease, and so given that information, it's just the probability that I test positive or negative. So if the probability I test negative is 0.92, then the probability I test positive is going to be 1 minus 0.92, which is 0.08. And once I do that, I have all the numbers I need and I can plug them in. So let's do that. Probability of positive test given you have the disease is 0.95. Probability of having the disease in general is 0.01. Probability that you test positive given you have the disease times probability you have the disease. Oh wait, that's the exact same thing we just did. So let me copy that down. Add to that the new thing we had to figure out, probability you test positive given you don't have the disease, which was 0.08, multiplied by the probability that you don't have the disease, which is 0.99. Now I'm going to throw this stuff in my trusty calculator. So on top, I'm opening parentheses, and then I'm typing in 0.95 times 0.01. I'm closing these parentheses, hitting divide, opening a new set of parentheses, and now I'm doing 0.95 times 0.01 plus 0.08 times 0.99. Close my parentheses, hit enter, and I'm getting 0.1071 approximately. I am cutting off some digits there. And that comes out to be 10.7%. Now if you look at that, that's kind of small. I mean, I guess it's not super small. It's a little over 1 out of 10, but it's smaller than you'd think, right? Because you read this and it says, the test correctly identifies that you've got the disease 95% of the time. And it correctly identifies not having the disease 92% of the time. Those are pretty high, you know, it's over 90%. Intuitively, we want to look at that and go like, ooh, man, that's not good. I tested positive. But the thing is that when you actually go through this, what does this 10.7% mean? What it means is that out of all the people who have the disease, only 1 in 10 of them actually test positive. The rest get incorrectly identified. Or you could also say, out of everyone who's tested positive, only 1 in 10 of them, only 10.7% of them have that disease. So it's pretty common actually to not give certain tests. If the tests are going to give you false positives fairly often, like if it's a low probability that it actually means you have the disease, it might be more dangerous either to the mental health or just to like the treatment which would be involved for treating something that's not there might be too involved. So I'm more of a math guy. I can't get too into details about that, but just know that depending on what type of test is going on, maybe the probability that it was correct is not that high when you factor everything in. Either way, whether or not it has real-world application, this is Bayes' theorem, and this is how you would go through and figure out all your respective probabilities. Read this very carefully to realize what's your given and what's the actual thing that had a probability, and then use your 1 minus rules to get the other probabilities you need, throw them all in, and get your conditional result. And that is this example.